Let's begin our journey in the physics lab by exploring how to determine the resistivity of wires using Ohm's law. In this experiment, we use an ammeter, voltmeter, two unknown resistance wires, a rheostat, a battery, and connecting wires. The core idea is that the current flowing through a conductor is directly proportional to the potential difference across it, provided the temperature remains constant. By plotting a graph of potential difference versus current, we can calculate the resistance of each wire. With the measured length and radius of the wires, we then use the formula for resistivity, which involves the resistance, length, and cross-sectional area. Careful observation and calculation allow us to determine the resistivity for both wires A and B, with results typically expressed in ohm meters. This experiment not only reinforces the concept of Ohm's law but also demonstrates the practical process of measuring material properties in the lab. Next, we move to the meter bridge, a classic tool for measuring unknown resistance and verifying the laws of series combination. The meter bridge operates on the Wheatstone bridge principle, allowing us to find unknown resistance by balancing the bridge and using the appropriate formula. By adjusting the balance point and recording the corresponding lengths, we calculate the resistance of the wire. We also explore the series combination of resistances, where the total resistance is the sum of individual resistances. Through careful observation and calculation, we compare experimental values with theoretical predictions, confirming the laws of series resistance. This experiment emphasizes the importance of precise measurements and the power of bridge circuits in electrical analysis. Let's now focus on the galvanometer and assembling basic electrical circuits. The half-deflection method is used to determine the resistance and figure of merit of a galvanometer. By adjusting resistances and observing deflections, we calculate the galvanometer's resistance and its sensitivity. Additionally, assembling a simple circuit with a battery, key, ammeter, and voltmeter teaches us the correct way to connect components, ammeter in series, voltmeter in parallel. We also learn to identify and correct common connection errors. These foundational skills are crucial for accurate measurements and safe operation in any physics lab, ensuring reliable results in more complex experiments. Moving into optics, we explore experiments involving lenses, mirrors, and the behavior of light. Using a convex lens, we determine its focal length by plotting a graph between object and image distances. For a concave mirror, we use the UV method to find its focal length, applying the mirror formula. We also study the refraction and lateral displacement of light through a glass slab, observing how the emergent ray remains parallel to the incident ray, but is laterally shifted. Finally, we investigate the diffraction of light using a narrow slit, observing characteristic bright and dark fringes. These experiments highlight the wave nature of light and the precision required in optical measurements. Finally, we delve into the world of semiconductors by examining the IV characteristics of a p-n junction diode. In forward bias, the diode allows current to flow easily after a certain threshold voltage, while in reverse bias only a tiny current flows until breakdown occurs. By plotting the current versus voltage for both forward and reverse bias, we observe the distinct behavior of the diode, including the threshold and breakdown voltages. This experiment is essential for understanding how diodes function in electronic circuits, forming the basis for rectifiers and other semiconductor devices. Careful measurement and plotting reveal the unique properties of semiconductor materials.